Welcome to the lecture on 5.3 for divergence and integral tests. So just to get right into it, the divergence test is probably the easiest of all the tests and comparisons that we're going to do. So it's just the idea that if you have a series, then if the terms inside, if a sub n doesn't go to 0, then it's not possible for this thing to converge. So think about it. If you keep adding up number after number after number, and those numbers don't get small, then of course this thing's going to blow up to infinity or possibly oscillate. So the key thing that I see people often mistake is the following. So while it is true that if the limit as n goes to infinity of a sub n is not 0, then the series diverges. It's not true that if the limit does go to 0, then the series will converge. So for example, the harmonic series we saw last time diverges and the limit as n goes to infinity of 1 over n is still 0. So just be careful with similar statements that sound reasonable but aren't exactly the form for Theorem 5.8. Okay, so let's use Theorem 5.8 in the following example. So for A, we get that the limit as n goes to infinity of n over 3n minus 1. This is 1/3, which is not 0. So we know from that that our series will diverge. In example B, maybe I should write this first. So if we take the limit as n goes to infinity of n cubed, this does equal 0. But again, it's not, we can't say anything. If the limit is 0, we can't say anything regarding Theorem 5.8. So the divergence test is inconclusive. And for the last example, for n equals, why do I keep doing that? The limit as n goes to infinity of e to the 1 over n squared, this is going to be e to the 0, which is 1. So this is not equal to 0. Therefore, our series will diverge. So the next tool we're going to develop is the integral test. And this one, you have to check a few things. So first of all, you have a series, and you need to make sure that A is positive. So just to really highlight all the things that need to come into place before we can even apply this. So we need to have that A sub n is positive for all. By the way, we write for all as an upside down capital A. So it needs to be positive for all n greater than or equal to 1. You need to have a function f. we need f to be continuous, which I usually just write CTS. F needs to be decreasing. And f of n needs to equal a sub n for all n greater than or equal to some capital N. So this just means that after some point or time, after a while, that f matches a sub n. So once we have those things determined, then we can go ahead and use the theorem 5.9 for the integral test. So that is, if the integral from n to infinity of f of x converges, then so does the series, and vice versa. Also, if the integral from n to infinity of f of x diverges, then so does the series, right? So if you can get this going, then they behave exactly the same as far as convergence, divergence. Another thing to note, it doesn't mean that the integral and the series have the same value. Sure, they're both going to converge or both diverge, but when they both converge, they may have different values. All right, so let's give it a whirl. So we have to meet all of these conditions, right? So for the first one, we see here that a sub n is equal to 1 over n cubed. And this is positive for all n greater than or equal to 1. So check. Then the next thing we need to determine is our function f. So we're going to let f equal 1 over x cubed. So now what we get here is that f of n equals a sub n, right? So on every positive integer, the function matches the terms in the summand. And remember, this only had to be true for some integer value n, but this will start to be true right off the bat. So this is true for all n greater than or equal to 1. So here our capital N equals 1. F is continuous on the interval 1 to infinity. And then we also need to show that f is decreasing. So there's a couple of ways that we can show something is decreasing. The first one is my go-to. It's usually a bit easier in this section, but I have a fallback plan if it doesn't work. So to show that f is decreasing, let's say that x is greater than or equal to y. So if x is greater than or equal to y, then I want to show that f of x is less than or equal to f of y, right? So this is decreasing. The further out I go along the x-axis, the smaller the value of f gets. So f of x and f of y, that's 1 over x cubed is less than or equal to 1 over y cubed. And this is true because x is greater than or equal to y, right? So our denominator is much larger when you're x, and so this inequality holds. So we've got that, check. So now we can go ahead and use the integral test. We've satisfied all the conditions. So we apply the integral test. So remember, we had to know what that capital N was. So that was important because what we want to do is take the integral from n, capital N, to infinity. So it was 1. Our function is 1 over x cubed. And so to integrate that, I'm just going to get negative 1 over 2x squared. And I'm evaluating that from 1 to infinity. So this is an improper integral, and we know how to deal with these. So really, if I was being extra careful, I would write this. And as b goes to infinity, this is just 1/2. So you can conclude that since the integral converged, the series will also converge. And again, just to note, that even though they both converge, the series 1 over n cubed does not converge to 1/2. So next we have the P series. So this is another, I think last time I said the harmonic series is super important. You have to know this. The P series is just a generalization of that. So we've already seen 1 over n and 1 over n squared as a series. And these are examples of P series. But in general, any series of the form, the summation of 1 over n to the P is called a P series. And we know that P series converge whenever P is strictly bigger than 1. And we also know that P series diverge whenever P is less than or equal to 1. So this is just something that you'll have to store in your mental arsenal. All right, so let's use the definition of a P series and what we know about its convergence and divergence properties in this example 515. So in A, we see that P equals 4. 4 is bigger than 1, therefore 1 over n to the 4th converges. Again, we're not saying what it converges to. We don't do that very much in calculus too, actually. And in B, we have that P equals 2/3, which is less than or equal to 1. Therefore, the series diverges. And so lastly, what we want to do is now we want to estimate the value of a series, or at least say how good of an estimation we're getting. Because it would take a very long time and we'd all be dead if we had to sit around and count up all the terms for an infinite series. So sometimes we'll just be like, okay, maybe I'll just estimate it by, the first 10 terms. Or maybe I'll estimate it by the first 100 terms. And the idea here is to say, okay, if I use that estimation with a partial sum, how good of an estimation is it? And so we have a really cool way of doing that, and it relies on the integral test. Because it relies on the integral test, we still have to meet all those conditions where f is continuous, it's positive, it's decreasing, it matches the series, and then the series itself is full of positive terms. So the key thing here is R sub n. So notice that R sub n is the whole series minus the first n terms. So the idea is that if the first capital N terms, you think they'd get a new letter. Anyway, if the first capital N terms is used to approximate the series, then all the terms after that, so that's capital N plus 1 all the way up to infinity, that's all the leftovers. Which we call the remainder. Right, so from little n going to capital N plus 1 up to infinity, that's just this. Right, if you have your entire series and you take away the first n terms, then you can just start at the n plus 1th term. So now that we kind of have an idea of what the remainder is, Theorem 5.10 is going to show us how to estimate the remainder. So again, series A sub n, we are using convergent series, otherwise the remainder, it's going to be an infinite, or the series itself will not converge and it's not really useful. So you get your f, right? It matches the series, it's decreasing, it's continuous. And then we let S sub n, this is the nth partial term, right? So remembering that S sub n is just the first n terms, right? So this guy is S sub n. Then what we can say is that the nth partial term plus the tail end using the integral, right? So instead of, because we can integrate and get a number for this nicely, and because the series converges, we know this integral also must converge. So if we kind of approximate it using the kind of leftovers, but in the integral form of it, then this will give us a bound on our error. In particular, if we just subtract off, like, so here's the derivation. So you have f sub n plus the integral from n plus 1 to infinity f. So if you subtract s sub n from both sides, then what you would get is just the integral from n plus 1 to infinity Right, and so S sub n is just the first n terms. So this is just n equals capital N plus 1. And this is just Rn, right, the remainder. So that's where that comes from. So we are going to use this to estimate the value of a series. All right, so in A, our series is well, for the entire example, the series is this. So maybe let's just set up the whole thing. So we have A sub n, which is 1 over n cubed. And we already went through this, right? We said A sub n equaling 1 over n cubed is positive for all n greater than or equal to 1. And then we had that our function f was equal to 1 over x cubed, so that f is continuous, f is decreasing, right? We showed this before, and that f of n equals 1 over n cubed. Maybe I'll write it like this so it's clear. F of n equals a sub n for all n greater than or equal to 1. And so that's where capital N was equal to 1. Maybe I'll leave that bit off. You know, there's 26 letters in the alphabet, plus the Greek alphabet. And I feel like N is getting a lot of action and other letters are being not appreciated. It would be helpful to have something other than N. Anyway, I digress. So what we want to do is first calculate S sub 10 and estimate the error. So this is just going to be the first 10 terms. So from n equals 1 to 10 of 1 over n cubed. So that's 1 over 1 cubed plus 1 over 2 cubed. Etc. and so on, all the way up to 1 over 10 cubed. So TV magic, this is approximately 1.19753. Okay, great, super. And now we want to estimate the error, right? So we know, we've already seen that 1 over n cubed converges. We don't know the value to which it converges, but right now we just have this estimate S10. So, you know, it's probably a decent estimate, but we want to know how far off we are. So in order to determine the error, we have R sub 10, right? And we know that R sub 10, we're just going to use the upper bound, right? So I don't care that the error is bigger than this guy. It may come into play later, but I do care that the error is bounded above. I'm going to use this. Just the right half of it. I do care that the R sub n is bounded above. So I know that R sub 10 is strictly less than the integral from 10 to infinity of 1 over x cubed dx. So all we have to do is just compute this integral here. So as b goes to infinity, this will be 0. And so what we're left with is 1 over 200, which is equal to 0.005. So now I know that my error can be estimated by 0.005. And that's the worst that the error can be. It may be the case that the error is a bit smaller, but typically when you're doing things like error, you always want to say the max possible error. So in the next part of this problem, we're kind of going to do it backwards. We want to know how far out we have to go in order to achieve a certain error threshold. So like, let's say you're manufacturing for, I don't know, some sort of like production line or something like that. And you need to make sure that your error is within 0.001 millimeters, like maybe you're making widgets or something, and if it's beyond this error, then the parts won't fit, and then, you know, you're fired, company goes under. So that's like a sort of real world application. So in B, we need to know how far out we need to go to get the exactness that we need. So we want R sub n to be less than 0.001. That's really all they're asking. Right, so if R sub capital N is less than 0.001, then what is n? Well, we know that R sub n is less than the integral from capital N to infinity of 1 over x cubed dx. So I can just work with this guy here in very much the same way. So maybe I'll kind of skip the fanfare of all of my limits and whatnot. So this equals the limit as b goes to infinity of -1 over 2b squared plus 1 over 2n squared. And so taking the limit of that, I just get 1 over 2n squared, right? So this is my upper bound for my error. So now what we need to do is just solve the inequality that we were given, right? So kind of coming back here, I want this to be true. So what I'm going to do is set that up. I know R sub n is, the worst it can be is 1 over 2n squared. And I need this to be less than 0.001. So you just go ahead and solve the inequality. So this becomes 2n squared is bigger than 1,000. So n squared is bigger than 500. Take the square root of both sides. N has to be bigger than, I want to say 2236. Yeah. So Then the last step is just to realize that n is an integer. So you can't go down to 22 because then you may not meet your error tolerance. So always round up to the next biggest integer. Like even if n we got was 22.00000001, we would still have to start at 23 because we have a strict inequality. So you're not even rounding, you're just going to the next highest integer. It's called a ceiling function, by the way. It's very cool. So that is it for section 5.3. And good luck.